Okay, Matt Roscoe here at the University of Montana, Section 3.3, the chain rule in our course, Math 570, Calculus for Middle School Teachers. Today I want to give you a quick motivational example of the chain rule and how it flows from ideas about ratios, and then go on and state the chain rule and give you 3 or 4 examples as well as an applied example. So here's the motivational example. Suppose that you're in a hot air balloon rising above the ground where the temperature is 75 degrees Fahrenheit. The balloon's rising at a rate of 50 feet per second. As the balloon rises, the temperature drops at a rate of 5.4 degrees Fahrenheit for every 1,000 feet above ground. How is temperature changing with time? Okay, so let's think about that for a second. If If we are to work this problem, let's think a little bit about how we do it. Let me get rid of this. We have, let's see, a setting where we've got a hot air balloon rising above the ground, temperature 75 degrees. So I guess let's identify the variables first of all here. We've got rising above the ground, so I guess we'll let h be equal to the height above ground. Let's let t be equal to the time, I guess, in seconds. And let's let f be equal to the temp in Fahrenheit. F A-H in height. Okay, so these are our variables. What we're told is we're told 2 rates. In a sense, what we're told are 2 derivatives which are constant. So we're told really that the time rate of change of the balloon rising 50 feet per second. So really what we're told is that the rate of change of height, dh, with respect to time, dt, is 50 feet per 1 second. So dh dt, 50 feet per second. The other piece that we're told is that the temperature, so df, with respect to distance above ground, dh, is equal to, well, it's falling at a rate of 5.4, so it's going down 5.4 degrees Fahrenheit for every 1,000 feet that we change. Okay. So so the big question is how is temperature changing with respect to time? So what we're really looking for, can we use these ingredients to find something like df, the change in temperature in Fahrenheit with respect to time, dt. And I hope your intuition is that we've got a df dh here, a dh dt here. So if we somehow just multiplied these 2 rates, the h on top here and the h on bottom here would cancel, and we'd get a df and a dt in the respective positions where they need to be. So let's try it. What would be df? dh times dh dt give us, well, df dh is negative 5.4 over 1,000. dh dt is 50. Oh, and I should put this as degrees Fahrenheit, and this is feet. And we'd multiply that by 50 feet per 1 second. And you can kind of think of this as units canceling. The feet and the feet seem to cancel here, and we get degrees Fahrenheit per second. So I have 5.4 negative times 50 That all divided by 1,000. So I get negative 0.27. Let's think about what the units on it are. It's degrees Fahrenheit per second. And that's really what the instantaneous rate of change of temperature with respect to time is. It's this thing, right? And this should give you some intuition now into the chain rule now when we go to its formal statement. So let's go to its formal statement now and take a look. I'll make this bigger. So the formal statement of the chain rule says that if we've got two differentiable functions, an f and a g, where one is inside of the other, so when we're inside one function inside of the other or nested inside, sometimes we call that a composition of functions. And if that's the case, then the derivative of a composition of functions is the derivative of the outside function, the one that's on the outside, leaving the inside function alone, times the derivative of the inside function. So the derivative of the outside with the inside left underived, I guess, and then the derivative of the inside function. So in Leibnizian notation, if y is a function of z and z is a function of x, then both are differentiable functions, then to find the derivative of y with respect to x, what we do is we multiply the derivative of y with respect to z times the derivative of z with respect to x. So somewhat similar to the hot air balloon setting if we think of it in Leibnizian notation, although I think it's easier from an algebraic standpoint to think of it in the Newtonian form. So I'll mostly refer to this definition on the top, but keep in mind that what we really are doing is just what we're doing down below here. Two rates of change, one with the outside function, one with the inside function, where the inside function is playing a role in the first derivative there. Okay, so let's try this and see if we can generate a few examples of this at work. So I'll start with the problem statement of black. M of x is equal to x minus 3 quantity squared. And what I'll do in red is I'll identify where I'm applying my thoughts using the chain rule. The first thought I should have is right away, can I think of it like this? Can I think of m of x as an f of g of x? That is a function g of x inside of a function f of x. And when you look at this function, you can right away see that sure, f of x, the outside function, is just x squared. It's something squared, right? And g of x is the something that's inside that's being squared. So g of x is going to be equal to the x minus 3, the thing that's inside. So you should agree with me now that f of g of x is this function inside of that function, which is what m of x is. Okay, knowing that I'm going to use the chain rule now to do this, I should probably just go ahead and compute their derivatives because I'm going to need them. So I'll compute or carry out the differentiation. Okay, so now we are done thinking about this in terms of the setup. Let's now go after the derivative. So m prime of x is going to be the derivative of f of g of x, which using our notion of the chain rule, that's f prime of g of x, the derivative of the outside function, times the derivative of the inside function. Okay, so now I can go after this to find its derivative. F prime of g of x, well, f prime of x is 2x, but where I see an x, I should put g of x in, so 2 times x minus 3. And then I multiply that by g prime of x. Oh, I made a mistake. G prime of x is not x, it's 1, isn't it? Why didn't anybody say something? Huh. So here we go. G prime of x is going to be just 1. So it looks like our derivative, if we distribute the 2, is 2x minus 6. So that's an example of the chain rule in action. The derivative of the outside, so the 2 comes out in front, we lower the exponent by 1 and we get a 0 here, leaving the inside function alone, and then take the derivative of the inside function, which is just a 1. So our answer is 2x minus 6. I'm sure many of you have been thinking, well, why don't you just square out the binomial? That'd be a lot easier to deal with. Let's go ahead and use that as a check. So if we let m of x be equal to x minus 3 squared. Well, that's the same thing as x squared. Let's see, minus 3x, so minus 6x plus minus 3 squared, so 9. Here we can just apply what we already know to a polynomial. We'd get 2x minus 6, and sure enough, you get the exact same derivative. Seems like we went the long route over here on the right, whereas we could have gone a shorter route here by doing a little algebra up front. That's not always the case, and that's my plan in the next example to show you what if in the next example we had something like n of x is equal to the quantity x squared minus 3 all raised to the 99th power. Well, here's a case where you simply wouldn't want to do something like squaring out the binomial, because you'd have to write 99 binomials, and this would get messy. You'd have something with a huge number of terms, and very likely to make an arithmetic error, expanding this. So the better way to go about it is to apply what we know about the chain rule, to write this as f, or to think of this as f of g of x, where f here is going to be the outside function. It's just x to the 99. So f prime of x is going to be the derivative by the power rule, 99x to the 98th. And g of x is going to be the inside function, x squared minus 3. So g prime of x is just a 2x, isn't it? Okay, so now that we have those pieces, we're set to go for the chain rule. N prime of x is going to be, well, we're going to apply the chain rule here, f prime of g of x times g prime of x. Okay, so when I apply the chain rule, it's simply a plug and chug from these parts and pieces up here. F prime of g of x, it's f prime is going to be equal to 99 times x to the 98th, but x is in this case g of x, so it's x squared minus 3 to the 98th power, times the derivative of the inside function, which is g of x here, it's just 2x, and that would be your derivative. Now you could simplify this if you'd like. 2 times 99 is 198, so 198x might be a better way to write this. But that would be perhaps a nice simple way to leave it. So certainly in an example where you wouldn't want to do some expansion and apply earlier rules, it's much easier to do the chain rule here. Let's try another one. What if we did, what was this one? This is h of x, and it's equal to the square root of 2x squared plus 3x minus 5. So right away I think, well, I know I have power rules, and so let's use the power representation of square root. So 2x squared plus 3x minus 5 raised to the 1/2 power. Now I can see certainly this is the case where we can think of this as f of g of x, where f of x is equal to x to the 1/2. So f prime of x is going to be 1/2 out in front, x to the 1/2 minus 1, or negative 1/2. And let's see, g of x is going to be equal to 2x squared plus 3x minus 5. So g prime of x is going to be 4x plus 3. We've got all our ingredients. Let's go after our derivative now. H prime of x is going to be the derivative of the outside times the derivative of the inside. Okay, so derivative of the outside is 1/2. I'm going to write equal over here because it's going to get long. 1/2 x to the negative 1/2, but x is g of x, right? So 2x squared plus 3x minus 5 to the negative 1/2 times g prime of x, which is 4x plus 3. So this would be your derivative. We could write it a little nicer. We don't usually like to have negative exponents, so let's write it above and below. So we'd have 4x plus 3 on top. We'd have a 2 down below times the square root of this term, 2x squared plus 3x minus 5. So a perfectly good way to leave that particular answer. Let's try another one. What if we had j of x equal 1 over x to the 5th minus x to the 3rd. Again, some algebraic adjustment here might be in order. I would probably use an exponent. If I wanted to move this whole term into the top, I'd have to write it with a negative exponent. So x to the 5th minus x to the 3rd, all raised to the negative 1, would be equivalent to 1 over that binomial. And now I can see that it's easily thought of as a composition of functions, where f of x is equal to what, x to the negative 1, so the derivative there is going to be negative 1x to the negative 2, and g of x is equal to x to the 5th minus x to the 3rd, so g prime of x is going to be 5x to the 4th minus 3x squared. All right, so we've got the functions we need. Let's go after its derivative. G prime of x is going to be, when I think of the chain rule in generic form, f prime of g of x times g prime of x. So what does that mean here? F prime is going to be negative 1 times g of x, x to the 5th minus x to the 3rd to the negative 2 power. So that's f prime of g of x times g prime of x, which is this 5x to the 4th minus 3x squared. So we got a negative exponent here again, and a negative multiplier. This will stay on top. I'm going to apply the negative to this one to switch some things around. So what will that give us? It'll give us 3x squared minus 5x to the 4th. I just apply the negative 1 to that term, and I'm going to write this all over x to the 5th minus x to the 3rd quantity squared. I do see that there's some common x's top and bottom, and we'd probably be able to suck those out and cancel them. I'm out of whiteboard space, so I'll let you continue on the algebraic simplification. But in terms of the application of the chain rule, we're kind of at the point where now we're just simplifying algebraically. So let's move on and conserve time. So j of x done. Let's try k of x. This is e to the 4x. Well, right away you say, well, come on, Roscoe, we've already done these ones. This is in the term, in the form e to the kx, which we think has derivative from previous terms, k times e to the kx, so 4 times e to the 4x. We think that's the derivative from our exponential chapter, but let's just go ahead and think about it in terms of a chain rule setting. So, one of the things you can kind of think of here and see, we'll use it as a check to see if that's actually true. You could think of this as an f of g of x, where here the f of x function is going to be just the e to the x function, and inside of e to the x we have a g of x function, which is 4x. So 4x is inside of the exponential function. Here we know the derivative of the exponential function is just the exponential function, and here the derivative of 4x is just 4. So that means that we should be able to write the derivative of k of x as f prime of g of x times g prime of x. And in this setting, f prime of x is going to be e to the x with e to the 4x, because we're doing f prime of g of x, and then we multiply by g prime of x, which is just 4, and of course we get the same answer as we got before, 4 times e to the 4x. So it does indeed work to verify our previously developed rule for differentiation of functions of form e to the kx. Okay, let's take a look at one more example problem, and we'll end here. If world population can be modeled by this function, calculate P14 and P prime of 14. Okay, so let me write the function down. P of t is equal to 6 times e to the 0.013 Okay, well, what is P of 14? Well, let's see. P of 14 is going to be 6 times, let's see, e to the x, e raised to the point 0.013 times 14, and that's 7.197 roughly. Okay, so let's just talk about what that number is. So P is the population in billions, 14 after 1999, so 1999 plus 14, 2013. Looks like that's the population in 2013 and that the model predicts. So this would be 7.197 billion people in 2013. Okay, so let's find out what P prime of 14 is. To do that, we need to know what P prime of t is. Okay, I can see that I have something 6 that we can think of as an a constant times an f of g of t, right? So let's see, the constant function can come out right out in front. I'm going to do this one a little bit, and then we take the derivative of the outside, or the outside function is e to the x. So we take that derivative leaving the inside function alone, so it'll be e to the 0.013t, and then we multiply that times the derivative of the inside function, and the inside function, of course, is this piece inside, 0.013t, so the derivative of that is 0.013. because we're taking the derivative with respect to t. So I've got a 6 and a 0.013, so I'll multiply that together, 0.013, and I get something in the neighborhood of 0.078 e to the 0.013t. Okay, we've got a derivative function now that we obtained via the chain rule. Let's go ahead and evaluate it at 14. So if I plug 14 in there, so that number times e to the point, 0.013 times 14. What I'm getting is a 0.093, I don't know, 6. And let's think about this. If population's on the y-axis and time's on the horizontal, then that's billions of people per year. So it's a rate of change in year 14. So if we think of it as billions, and it doesn't make much sense to talk about hundreds of billions, what I'd probably do is move this 3 units to the left and talk about millions. So we're roughly adding 93.6 million per year in 2013. And that would be the contextualization of P prime of 14. Okay, well, I hope that you learned a little something about the chain rule here and population growth, and I look forward to your questions, and good luck on your homework.